In this next video, we're going to kind of pick up where that YouTube video I showed left off. So, someone has performed an experiment or calculated a rate of reaction for ozone, um, the reaction of ethylene and ozone creating photochemical smog. So we've got this ethylene, the C2H4, reacting with ozone, so O3, and producing this photochemical smog. Okay. And so what they've done is they've taken the concentration of O3 at specific time periods. So if you look at the data table over here, you can see that every 10 seconds, they've looked at the concentration of ozone. So as you can tell, because ozone was a reactant, there has been a decrease in the concentration of ozone. Sorry, I lost my words there for a second. Ozone over time. So then they took this data and they graphed it. So at time 0, the concentration of ozone was 3.2 times 10 to the negative 5. At 10 seconds, it was 2.42 times 10 to the negative 5. At 20 seconds, it was 1.95, and so on and so forth. And you can see with this, it's a curve, right? So they've drawn a line of best fit. There was no outlying data, and so the curve does follow the points pretty exactly. And now what we're going to look at is how could you then analyze this data? Or how could we determine from this data what is the rate of reaction? Well, there's three different ways that we can measure the rate of reaction from data. The first one is the one most commonly used, and it's an average rate. So what you would do is take the slope of a line for an entire duration of a reaction over a defined interval in a reaction. So for example, if you looked at this A, right? A is a straight line starting at time 0, 0, or starting at time 0 and concentration 3.2 times 10 to the negative 5, and ending down here at 60 seconds um, at a concentration of 1.1 times 10 to the negative 5. So it's this straight line path, not following the curve, that we could then find the slope of, and it would be an average rate. So let's do that first. Let's look at A. So A is calculating the average rate of the entire reaction. To calculate this, we would calculate slope. Now, hopefully you guys all know that slope is rate of change in the y values over the change in the x values. So for this one, our 2 points are going to be at time 0. We can just pull our data points from over here. So one of my points is going to be 0, 0 for my x value and 3.20 times 10 to the negative 5 for my y value. And then my other one is going to be after the entire reaction, so 60 seconds, where my y value is 1.10 times 10 to the negative 5. Okay, so then what we're going to do is we're going to plug this data in. Now it doesn't matter which one's y1 and which one's y2. I'm going to go this way, just because it's going to work really nicely with my time. So I'm going to do 1.10 times 10 to the negative 5 minus 3.20 times 10 to the negative 5 divided by 60.0 minus 0.00. Nope, sorry, just 0.0. So I'm going to do the subtraction before I do the division. So if we think about sig fig, so even though there's this 0.0 in here, when we subtract, we maintain precision. So 60.0 minus 0.0 is still 60.0. So we're going to answer to 3 sig figs. I'm going to plug this into my calculator. 1.1, now I have the EXP button. You might have an EE button, or maybe your calculator says times 10 to the. But I'm going to do 1.10 times 10 to the negative 5 minus 3.2 times 10 to the negative 5, and then hit equals. So you have to make sure that you tell your calculator that it has to do this calculation before it does this calculation. So for me, I plug in my numerator and I hit equals, and then I hit divided by, and it says answer divided by, and then 60. Then I'm going to answer to 3 sig figs, so I get negative, change back to blue, negative 3.50 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. And then make sure you look at your units. So my units for my Y values are moles per liter. and my units for my x values are in seconds. So my units for this would be moles per liter seconds, or maybe you want to write it as moles per liter per second, or maybe you realize that moles per liter is actually concentration per second. So any of those would really do. I tend to write it in whatever units are written on my graph. So I would prefer moles per liter per second or moles per liter second. It means the exact same thing. Okay, but A is a great example of an average rate. The next one is an instantaneous rate. An instantaneous rate is one where you're trying to look at a specific time. So, for example, D would be a great example of an instantaneous rate. If you look at this one, you've got this instant point D, and then they've drawn a line tangent to the curve at that point. And so we could find the instantaneous rate of reaction at point D by finding the slope of this line. Now, this one's a little bit trickier, so I'm going to erase what I drew because we have to try to estimate. So it's not like A, where we knew the defined beginning and end points. For this one, we're trying to go from here to here. So we're going to have to do a little bit of estimation of data. So the beginning and end of this line D, so if I look at this point here, we are going to read this as, what would I read this as? Maybe 22, like this would be 25. It's like almost 22 or 23. It's hard to say, so that's going to be my estimation. I'm going to say 20, 20, what do you guys think? 20, thinking 23. It's kind of closer to that 25 line. Okay, but I'm going to go 23. And then my Y value, I'm looking over here. So it's somewhere between 1 and 2. It's kind of about here. I'm going to put 1.8. And again, I can't carry as much significance because I am sort of estimating. And then this would be 1.8 times 10 to the negative 5. There's a bit of a typo in this graph. So this should be 10 to the negative 5. Okay. And then if we look at a coordinate of a point down here, so again, this is D. D is an instantaneous rate. And we're calculating the slope. I'm going to use my point 1.8 times 10 to the negative 5. And I'm going to use my time of 23. And then I've got to find two other points. So then my points here, we're kind of looking at maybe 48. So I'm going to go minus 48 seconds. And then my Y value there, carrying this across, this would be 1.5. I'm going to go 1.3 times 10 to the negative 5. Okay, and then again, we just plug this into our calculator, and everybody would have a bit of a different answer, but I'm only going to answer this one to 2 sig figs because of the accuracy of the graph I was reading off of. So 1.8 times 10 to the negative 5 minus 1.3 times 10 to the negative 5 equals, and then divide that by bracket 23 minus 48, unbracket, and I get negative 2.0 times 10 to the 1, 2, 3, 4, 5, 6, 7 moles per liter second. Okay, so again, that was an instantaneous rate at point D. The next one is an initial rate. So initial rate is the slope of a line tangent to a curve again, so just like instantaneous rate, but specifically right at the start of the reaction. So this would be E right here. So this purple line here is going through this point 0 and 3.2 times 10 to the negative 5, and then we'd find the slope of this entire thing. So if I was to use 2 points for that one, I'm going to use 0 and 3.2 times 10 to the negative 5. And then I'm going to use this point here is going to be something like, it's almost 10. I'm going to go, like, can we use 10? Let me erase this. Oh, it's not quite, hey? I'm going to go like 9. You shouldn't actually be able to record this with precision, but I don't want to say 9 and I can't say 10. Actually, you know what? I would say 10 over 9. Okay, we can't be precise, so I'm going to say 10. Oops. So I'm going to do my x value of 10, And then my y value is definitely 2.00 times 10 to the negative 5. Okay, so the 2 points that I'm going to use, I'm going to plug into my calculator. And this is for E. So E is an initial rate. And for this one, I'm going to use that initial point. So I'm going to start with my 0 and 3.2 times 10 to the negative 5 minus 2.00 times 10 to the negative 5. And then I'm just going to do minus 10. Yeah. Okay. So I'm going to plug in my calculator. 3.2 times 10 to the negative 5 minus 2 times 10 to the negative 5 equals divided by negative 10, which leaves me with negative 1.2 times 10 to the negative 1, 2, 3, 4, 5, 6 moles per liter. Moles per liter seconds, or moles per liter per second. Awesome. Okay, and then I just have 1 point left here at C. So C is down here, and I want you to pause the video and think about this. Is C showing an average rate over a defined interval, an instantaneous rate, so the slope of a line tangent to a curve at a specific time, or an initial rate, so the slope of a line tangent to the curve right at the start? So hopefully you know that this is going to be average rate. I'm just going to zoom out. So this one is also going to be an average rate over a specified time interval from 50 seconds to 60 seconds. So for this one, I can just use my data points. So I can look at my chart. So 50 seconds to 60 seconds, I can do 1.10 times 10 to the negative 5 minus 1.23 times 10 to the negative 5 divided by 60.0 minus 50.0, which is going to give me what? So 1.1 times 10 to the negative 5 minus 1.23 times 10 to the negative 5 equals divided by 10, which leaves me with negative 1.30 times 10 to the negative, I'm going to guess 7. 1, 2, 3, 4, 5, 6, 7. Yep. Moles per liter second. So we've calculated 3 rates of reaction. We've got our initial rate at E, which started off at 1.2 times 10 to the negative 6. Then we did an instantaneous rate at D, which was negative 2.0 times 10 to the negative 6. And then we did an average rate C for the last 10 seconds of the reaction, where the reaction rate was negative 1.3 times 10 to the negative 7. Overall, the reaction rate was negative 3.5 times 10 to the negative 7. So what does all of this mean? Well, all of this means that what is happening to the rate of reaction over time? Well, we started at negative 1.2 times 10 to the negative 6. We ended with negative 1.3 times 10 to the negative 7. So the rate of reaction is decreases. So it's decreasing over time. Why? Because you are using up the reactant. So a reaction should always slow over time because you are using up the reaction. And if you think back to that YouTube video, she got to a point where no more gas was being produced, and so she actually should stop her reaction. Awesome. So go and practice this 1.4, which is measuring reaction rates using data. There's some great Hebden questions as well as questions on the worksheet.